Hello everyone, welcome to the channel. In this video, we officially start our journey into linear algebra. Linear algebra is the study of vectors and linear functions. Today, we'll begin with two very basic but extremely important concepts, scalars and vectors. They're simple, but they're also very powerful. You might ask, why do we need linear algebra for machine learning? The answer is simple. Machine learning works with numbers, data, and models, and linear algebra is the language that connects all of them. Once you understand linear algebra, many machine learning formulas suddenly start to make sense. Let's start with the simplest object, a scalar. A scalar is just a single number, nothing more, nothing less. 2 minus 5, or 3.14 are all scalars. Every real number is a scalar. Even though scalars are simple, they play a very important role in machine learning. For example, the learning rate, the bias term, or the loss value are all scalars. Think of the learning rate as the step size. In the journey to find the best answer, it controls how much we adjust our model in each step. A high learning rate might overshoot the goal, while a low one makes the process painfully slow. Bias is an offset scalar. It allows the model to shift its prediction up or down. Without bias, a linear model would always have to pass through the origin 0, 0, which isn't realistic for most real-world data. It provides the flexibility to fit the data better. The loss value is a single scalar that measures how wrong the model is. It calculates the distance between the predicted output and the actual target. In machine learning, our entire goal is to minimize this single number. In linear algebra, a scalar might seem like just a simple number, but in machine learning, these scalars are the knobs and dials we turn to train a brain. One scalar controls speed, which is the learning rate. One controls position, which is the bias. And one tells us how successful we are, which is the loss. These single numbers control how a model learns and behaves. Now let's move on to vectors. A vector is a quantity with magnitude and direction, visualized as a directed line segment just like an arrow. Vectors have different meanings in different fields. In physics, they're arrows like force and velocity. In computer science, they're lists of numbers. And in mathematics, they're the basic objects of linear algebra. For example, imagine we want to describe a house. We can use size, number of rooms, and age. These three numbers together form a vector. In the world of machine learning, vectors are everywhere. If linear algebra is the language of modeling, vectors are the words. A vector is essentially a digital ID for any object, whether it's an image, a word, or a user profile. To understand vectors is to understand the very heart of data representation. For example, a data sample is a single observation or object. If you have a data set of houses, each individual house is a sample, represented as a vector in space. Features are the individual properties or attributes of a sample. These are the numeric values, scalars, inside the vectors like area, number of rooms, or price. Each dimension of the vector corresponds to one feature. A gradient is a vector of derivatives. It acts like a compass, pointing in the direction of the steepest increase. In machine learning, we use the negative gradient to know exactly how to change our weights to reduce the error. Now, let's talk about a powerful concept called embedding. Sometimes, data is too complex for a simple list of numbers. Think about words, images, or even human emotions. We can't just put the word apple into an equation. We need to turn it into a vector. An embedding is a way to represent complex data as a vector in a way that preserves meaning. In an embedding space, the distance between vectors represent how similar they are. For example, the vector for king will be very close to the vector for queen. The vector for apple will be very close to orange but very far from car. So when we talk about embeddings in linear algebra, we are talking about mapping a concept into a multidimensional space where its location actually means something. It's like giving every idea a specific address in a mathematical city. So when we study linear algebra, we aren't just playing with numbers. We are learning how to package real-world attributes, features, into vectors, samples, and use a mathematical compass gradients to find the best path for our model to learn. You may be familiar with 2- and 3-dimensional vectors. Vectors in 2-dimensional real space are 2, and the 3-dimensional real space are 3. For example, a 2-dimensional vector x equals the vector 1, 3 could describe the position of your feet in meters north and west of the corner of a room. A 3-dimensional vector x equals the vector 1, 3, 1.5 could describe the location of your head, with the third dimension corresponding to the distance from the floor. We can generalize this concept to an arbitrary number of dimensions, say n dimensions. We refer to an n-dimensional vector as a vector in Rn and write it as an n-tuple of numbers, x equals x1, x2, x3, and so on up to xn. For example, 1, 6, minus 23, 0.23, 0, 400 is a vector in R6. How many dimensions does it take to specify the position of a rigid object like an airplane in space? At first, you might think 3 dimensions are enough. 1 for the x-coordinate, 1 for the y, and 1 for the z. And that's partly true. 3 dimensions are enough to specify the center of the object. But there's more. Even if we know the center, the object can still rotate. For an airplane, for example, it can roll, pitch, and yaw. 3 different rotations. So in total, we actually need 6 dimensions to fully describe the position of a rigid object. 3 dimensions for the location of its center, and 3 more to describe the direction it's pointing. If we consider non-rigid objects, the number of dimensions needed to describe their configuration can get pretty high. For a simple example, let's look at this little stick figure. To specify the angle of its arms, legs, and head, we need a vector in 9-dimensional space. We call this the configuration vector, written as theta vector equals theta 1, theta 2, theta 3, until theta 9. You can imagine sliders that you can drag with your mouse to change each component of the vector. Theta 1 and theta 2 control the angles of the left arm. Theta 3 and theta 4 control the right arm. Theta 5 through theta 8 control the left and right legs. And finally, theta 9 controls the angle of the head. High-dimensional vectors show up even in neuroscience. Imagine recording 100 neurons from a lab rat named Fred at the same time. That's a 100-dimensional vector just for one moment. If we record for 10 minutes and sample 1,000 times per second, we end up with a 60 million dimensional vector. Clearly, a simple 3-dimensional vector is enough for many real-world situations. And of course, it's better to record from a rat than from children with severe epilepsy. Imagine if science could find ways to avoid that altogether. Now let's talk about basic vector operations. These operations are the foundation of almost every algorithm in machine learning. Let's start with vector addition. Suppose we have 2 vectors, vector A and vector B. To add them together, we simply add their components one by one. So the sum of A and B is a new vector, whose first component is A1 plus B1. The second is A2 plus B2, and so on. Geometrically, vector addition means placing the tail of one vector at the head of the other. The resulting arrow represents their sum. Now let's look at vector subtraction. Subtracting vector B from vector A means subtracting each component. Geometrically, vector subtraction answers a very useful question. What vectors take me from B to A? In machine learning, we constantly add and subtract vectors. We subtract predictions from targets, update parameters, and move step by step towards better models. Now let's move on to three extremely important operations: scalar multiplication, vector magnitude, and the dot product. Scalar multiplication means multiplying a vector by a single number. Each component of the vector gets multiplied by the scalar. Geometrically, this operation changes the length of the vector. If the scalar is large, the vector gets longer. If the scalar is small, the vector shrinks. If the scalar is negative, the vector also flips direction. Finally, let's introduce the dot product. The dot product takes two vectors and returns a single number. This number captures how similar the two vectors are. Dot products appear everywhere in machine learning, in linear models, in neural networks, and also in similarity measurements. Whenever a model compares data with its parameters, a dot product is usually involved. Key meanings are: measures similarity between vectors, used in projections and angles, core operation in neural networks. If the dot product is large, the vectors point in similar directions. In machine learning terms, this tells us that two pieces of data are similar. A word is related to a certain concept, or a data sample matches the direction of the model's weights. Now let's talk about the magnitude, or length of a vector. The magnitude tells us how far the vector is from the origin. In machine learning, vector norms are used to measure distances, control model complexity, and stabilize training. Effect is changes the length of the vector and keeps the direction, or reverse. The length or size of a vector is called its norm. The norm measures how far the vector is from the origin. In machine learning, it is used in regularization and measures distance and similarity. Now, let's look at the geometric meaning of the dot product. So far, we've defined the dot product as a formula, but it also has a very powerful geometric interpretation. Suppose we have two vectors, vector A and vector B. The dot product can be written as the magnitude of A times the magnitude of B times the cosine of the angle between them. That angle, usually denoted by theta, is the angle between the two vectors. Now here is the key idea. The dot product tells us how aligned two vectors are. If the angle between the vectors is 0 degrees, they point in the same direction. In this case, the cosine is 1, and the dot product is as large as possible. If the angle is 90 degrees, the vectors are perpendicular. The cosine is 0, so the dot product is 0. This means the vectors are orthogonal, or completely unrelated in direction. If the angle is 180 degrees, the vectors point in opposite directions. The cosine becomes negative, and so does the dot product. There is another important way to think about the dot product. You can interpret it as a projection. It answers the question how much of one vector lies in the direction of the other. So remember this: vector addition and subtraction moves us through space. Scalar multiplication controls scale and direction, and the dot product measures alignment and similarity. These operations together form the mathematical engine of machine learning. Now, this is extremely important in machine learning. When a model computes a dot product, it is effectively asking, how similar is this data to my parameters? This idea appears everywhere, in cosine similarity, in embeddings, in neural network layers, and in linear classifiers. So the dot product is not just a mathematical operation, it's a geometric tool. It tells us about direction, alignment, and similarity. Once you understand this geometric meaning, many machine learning formulas suddenly start to make sense. Why vector operations are fundamental? Vector operations are the mathematical engine behind gradient descent, linear models, neural networks, embeddings, and similarity search. If you understand these operations, you understand how models learn. If you found this video helpful, don't forget to like and subscribe to the channel.